Right, thank you. I was hoping I'll get additional 5 minutes, but you ate away 10 minutes.
No, I didn't.
No, I'm just joking. Right, yeah, but you started early. Right. Good. Yeah, thank you, organizers, for giving me the opportunity. So I do not know what title I gave, but I'll be talking about Metamaterials, about my work. I'm currently at NPL, so I have the obligation to give a little bit about what NPL is, and then I'll show work which is being done at NPL as well as at TAFR. Right. So National Physical Laboratory of India is the National Metrology Institute. So each country has one metrology institute designated. So NPL India is the metrology institute for the country. Right. So we do set up standards and make them available for the country for legal metrology and other purposes. Most recently, in last year, we have been given the mandate. We are always the timekeepers of India. So we've been given additional responsibility by certain that all entities like banks or whatever, like so networks, they all have to take the Indian Standard Time from NPL. So we have 6 divisions, physical mechanical metrology, where we do force, temperature, mass, and all these standards. In electrical and electronics metrology, we have the Josephson voltage and quantum Hall resistance, and we also look DC, AC, electrical metrology. So in environment and biomedical metrology, we maintain one of the Maitri stations in Antarctica, and we also do a lot of environment monitoring, equipment development, as well as doing the ionospheric modeling, climate modeling, and other things. So in the biomedical metrology, we are looking at developing national standards for biomedical equipment, including the ones which are already set up in the last 2 years are the defibrillator. This is a infusion pump. So we're looking at incubators and other equipment. So waste to wealth for cyclic economy. So it's just not bio-waste or plastics. We also initiated the activity where we got 39 purity silicon from waste solar panels. So we're looking at enhancing it and then making it industry compatible process so that we can transfer the technology. Carbon materials is again very big. So from Agni missile cone to more recently, so we developed these fuel tubes for nuclear reactors. So under the brand name of Bharati Nirdeshak Dravya, we make these certified reference materials. Most of the people know about the NIST standard materials, standard reference materials. So India has, we have our own branded certified reference materials called BNDs. We have for precious metals, gold, silver, rice, water, chemicals, cement, oils. So we have about 150 CRMs or the BNDs in the country available. These come at much a fraction of the cost compared to the imported CRMs. So as I mentioned, like, so we're also the timekeepers. So the Indian Standard Time is managed with between 2 to 3 nanosecond uncertainty. Right. So this is our cesium fountain. This is revived. So we are looking at contributing to BIPM soon. But right now this is revived. Right. So this is waste to wealth. Okay. So for this workshop, the important point is quantum metrology. There's always confusion. What the terminology is. Quantum metrology is the term referring to the redefined 7 SI units. So each of the, right now, for example, kilogram or meter, the kilogram is defined in terms of we have what is known as NPK, National Prototype for Kilogram 57. NPK 57 is India's standard kilogram. We make copies of it and then make it available. But there are uncertainties in it. So there is variation from year to year when we cross-check with the international prototype, which is at BIPM. So there is always some 20 microgram kind of errors in the mass value. So there are other issues. So these redefined terms or the SI units, each of them is defined with respect to a universal constant. For example, kilogram is now defined in terms of the Planck constant, and meter to speed of light, and etc. So the idea is that, like, we have to set these standards and then make them available for the country. So the status around the world is that if you look at mole Kelvin and all that, like, so the black ones, these countries already have these standards, the quantum standard. The ones in blue are the ones in Asia Pacific region, which already have these quantum metrology standards. And the ones in purple are the ones which we are still working on setting up these facilities in the countries, in our countries, right? So I mentioned that mass is related to the Planck constant, measurement of the Planck constant by using this Kibble balance. So the Kibble balance works and basically there are two modes in which we operate this and to remove all the uncertainties. So one is a dynamic mode in which so basically one arm has the unknown mass and then you have the coil on the other side, you apply current on it and balance it, and because we know precisely like what current is going into it, so we know what is electromagnetic force which is balancing the unknown weight on in the other arm. And to remove all these material related parameters like the coil length and the field and etc. So what we do is we move this dynamic mode operation where the coil is moved up and down, and then we see like how much field is induced in it. So from these two measurements, we take the ratio and then we cancel out the material dependent parameters, and then we get mass in terms of the Planck constant. So we made this first prototype for 1 to 10 gram Kibble balance. So we are currently working on 100 gram Kibble balance, and then eventually we had to go for the 1 kg balance. So right? G measurement, yes, that's true. It's required, yes. So this is for the Kelvin. So this is based on the acoustic gas thermometry. So this is an asymmetric cavity. We already designed and have this cavity. So now basically you put some known gas at constant pressure and temperature, and then you measure the velocity of RF passing through this cavity. Right. So this is probably Subhashish Panjasha, he would have shown you this. So this is the ytterbium ion-based optical frequency standard, which we are working on. Hopefully, he'll complete this soon. So coming to my own work, how do we go from this bulk room-filled vacuum chambers and pumps and all that to miniature chip size atomic clocks, right? So one of the ideas which we discussed with Umakant some 5-6 years ago, actually, it was his idea. He said that like, let us try out with the silver nano disc. So which, group like, so we optimized, we showed that gold is better than silver. So this is a potential profile on top of the gold disc or gold or silver disc. So these are the two curves which are shown. We optimize the disc dimensions for particular, for the rubidium atom, 780 nanometer, and then we also measured that, we measured the near field profiles and then mapped them to show that actually the potential profile exists for these. Right? But the actual atom trap experiments have not been done on this. So this was started, this was my first work, which I started with Hema when she was at RRI. So these were 3 gratings at 60-degree orientation. The idea here is that we launch light onto this, and then there are 3 beams which are coming up, and the diffracted beams will come up about 5 mm from the surface of the from the sample, so that we can use it for trapping. But however, later, like when after Hema sat demise, like so, these samples had given to RCI, and they measured it, and they gave feedback that this central region is also giving a spurious beam. So we moved on to a metasurface based one. So these are square cross-section silicon rods, which are, the dimensions are chosen in such a way that the phase of the incident beam is manipulated, so that initially we have 4 beams with feedback from RCI. Like, so we made it into 5 beams, modified it further to get equal intensity beams at about 3 mm from the surface of the sample. Right. So we made first set of samples. So we want this to be tested. Right. So where does this come in? So we look at manipulating the epsilon and mu of the materials. So we use a combination of different materials to get either like epsilon positive or epsilon negative or mu negative. We mix a combination of these things so that like we get functionality needed for any particular application. So negative index materials are well known, but metamaterials have a broader definition now with sub-wavelength featured scattering elements, which form the basis for making these materials for different applications. We have been working for about I don't know 20 years now, and both for physics as well as applications. So this is something which is similar to the first talk in this afternoon session. Like, so EIT, we have 2 quadrupolar resonances induced by the dipoles, which are at the top and the bottom. So these 2 quadrupole modes, they interact, and we showed that we can actually control the final resonance, and we could show highest Q factors at terahertz frequencies. So that's one thing. From application point of view, I'll show some applications. This is a stealth application. This is for a Yagi-Uda antenna for terahertz frequencies. So this is a spin to photon converter where you have a single quantum dot here. The electron spin defines the polarization of the emitted photon. By measuring output of 2 waveguides, we can actually reconstruct the spin state of the electron in this case. Right. So at the back of it, the basics is that like, so you have these particle plasmons, you have these free electrons which are on the surface of a metal sphere, for example, so which can oscillate up and down at a natural frequency. If the incident electromagnetic radiation frequency matches with this resonant oscillation, so there's a transfer of energy from applied field to the metal nanoparticle. So this resonance, the particle plasmon resonance, depends on the size, shape, and the medium in which these particles are embedded in. So similarly, you can have a metal and a dielectric interface. So the free electrons in the metal surface, they can be excited to have a charge density wave which propagates along this interface. So this is a surface mode, which means that away from the interface, you have these event-centrally decaying fields. And compared to the light line, so you have this dispersion of this surface mode is given by this expression, which means that there is a momentum mismatch. So directly by shining photons or light on an interface, metal dielectric interface, we cannot excite these plasmon modes. So people started structuring these surfaces, and that's how the metamaterials and metasurfaces came into, the plasmonic metamaterials came into popularity. So if you look at a simple grating, you take instead of having a flat metal, you make a grating structure. So you look at the dispersion profile, what you see is that the line width varies. So depending on the incident angle, so you have the same plasmon mode which is excited, but the lifetimes are not exactly the same. The dynamics are not the same. The plasmon dynamics are not exactly the same. So this is reflected in, for example, if you launch a short pulse, a short Gaussian pulse on a grating, and then you look at the reflection or the transmission, what you see is that depending on the lifetime of the plasmon mode, which are exciting A, B, C, or D, so you'll have different distortion in your short pulse. Right? So from this, we showed how to calculate the plasmon lifetimes and other things, so which is from the pure physics point of view. But interesting thing is that, like, if you want to use for short pulse applications, we want to have broadband dispersionless structures. So we showed that there are 2 ways to do it. One way is you take, for example, you want to cover 500 to 850 nanometer wavelength range. So you take different scattering cross sections, different shapes, and you can control them in such a way that, like, you put them in a square array, but randomly distributed scattering elements. So, and then you see that you get a broadband response. So in this case, we showed a broadband perfect absorber. So the geometry is here. So there is a patterned metal surface on the top. There is a thick metal layer. So in the in the electrical engineering parlance, this is the ground plane where nothing can transmit through this. And if you make sure that the reflection is suppressed, which means that there's nothing is transmitted, so you have 100% absorption within this thin layer, which can be few nanometers. So we showed that for about 10 nanometer thick silicon layer, we could get 99.86% absorption of the incident radiation, covering say 450 to 950 nanometer region. Right. So there is another way of getting broadband response, which is by going to quasi-periodic or random distribution. Right. Random distribution is not a unique solution, and repeatability is an issue. So we looked for quasi-periodic lattice. So this is a 5-fold rotation symmetry. So if you take certain number of scattering elements and put them in a square lattice, so you see the Fourier transform or the K-space is discrete resonances. But however, the same density of scattering elements, if you put them in 5-fold rotation quasi-periodic lattice, the K-space is very dense. You have different magnitudes of Ks, so you have a broad wavelength response. You have no polarization dependence and no launch angle dependence in this case. That's what we showed here. So this band will have dispersion-less plasmon modes are within this band. Right? So we showed that we can now launch plasmons, just shine light on this kind of structure where you have this top air gold interface and gold substrate interface. You can have two surface modes depending on the thickness. They can couple to each other, and you can have mode hybridization and other things. Right. So, but the important point is that like you have a strong local field at these interfaces, and now that can contribute to the weak, combined with the weak nonlinearity of the gold itself, and we showed that we can have broadband second harmonic generation from these structures, and because it's a thin film nonlinearity, there is no phase matching angle requirement in this case, right? So I'll briefly detour. So I'll just give something about some background of the light matter interaction. So most of our studies, most of the reports which you have seen, not most, like almost every single report which you have seen in this workshop dealt with this regime, which is a perturbative regime, where we study about the weak and strong coupling regimes, the Purcell effect in the weak coupling regime, or EIT, or in the strong coupling regime, you have the Rabi oscillations or splittings, anti-crossings, among other things. So I don't want to repeat the physics of it, like so, but basically in the non-perturbative regime, which is becoming more and more popular, so we are looking at cooperativity effects. So instead of having one single atom inside a cavity, we can have an ensemble of n dipoles within the cavity, and this leads to cooperative effects like enhanced coupling. So you can have novel effects which under this so-called ultra strong or deep strong coupling. So here the G is now comparable to the resonant frequency, unlike weak and strong coupling regimes, where G is comparable to the decay constants of the cavity and the two-level system. Right. So this is just a well-known math. Like so, you have the James-Cummings Hamiltonian under the rotating wave approximation is the perturbative regime, but we have to look for the full quantum Rabi model if you want to look at non-perturbative regime. Right. So these are just some of the effects which we are well known of. Right. So this is some examples of plasmon-mediated couplings. So here we have a grating where we excite the plasmon modes. If you put quantum dots on top, like so, you have resonant enhancement of this emission from the quantum dots, which is the Purcell enhancement of emission in this case. So you can also have a strong coupling anti-crossings, which are seen here. This is possible because of the plasmons which are propagating in plane. So I said that like, so you can have one plasmon mode here and one plasmon mode here, they can couple in the vertical direction. But in addition, you can have coupling of these plasmons or interaction of these plasmons within the plane. So that leads to these in-plane interactions and anti-crossings, which are signatures of the strong coupling in this regime. Right. So we wanted to look at, is it possible to go to non-perturbative regime? So we took this plasmonic structure, quasi-periodic structure with the broadband dispersion-less plasmon, so that the geometrical dispersion doesn't play any role in the dynamics. And we put different densities of quantum dots on top and looked at the spectral studies. So here, compared to the low densities, we see a blue shift of the peak, the emission peak. But the interesting thing is that, like, compared to the unpatterned metal, the patterned metal peak shows a red shift, which is the lamp shift. We do not see any splitting in this case. There is no Rabi splitting in this case, but then there is a blue shift of the thing. The interesting point is in the lifetime. So we see these oscillations in the short time scale. So this oscillation period basically matches with the shift which have seen in the spectral domain. Right. So the model which we are we did the full Rabi Hamiltonian calculations, and the idea the model which we are proposing is that, like, so we are exciting quantum dots on the patterned metal surface, and these quantum dots are emitting, which excite the plasmon modes, and these plasmons propagate and excite quantum dots at a faraway distance. So we have long-range dipole-dipole interaction mediated by the plasmons in this case. And from near-field studies, we show that indeed we do get emission from these quantum dots, which are almost like 20 micrometer away from the edge of this excitation spot. Right. So we calculated G by omega and all that. Like, so this is in the ultra strong coupling regime with G by omega is of the order of like 0.4. Right. So the other metamaterial which we looked at is a hyperbolic metamaterial. So if you have a homogeneous material, so we see the dispersion is shown by this spherical dispersion profile. So this is kx, ky, kz. So it's just a sphere. Right. So k is basically 2 pi over lambda n, or 2 pi n over lambda. So depending on the refractive index of your material, or epsilon and mu of your material defines what is the sphere diameter and all that, right? But we can manipulate this dispersion profile to have an inhomogeneous medium where the medium can be metallic in plane and dielectric out of plane, or vice versa. It can be metallic out of plane and dielectric in plane. So this is possible by I mean, in the effective medium models, like, we can have a combination of dielectrics and metals. So metals have epsilon negative and dielectrics have epsilon positive. So by combining these two, we can get these inhomogeneous media. So these have very unique dispersion profiles, like the hyperbolas. So which means that infinite Ks are also possible, or possible modes within these materials. So that makes it unique, because if you have a dipole emitter inside this structure, so you can effectively couple the emission or emitted photons into this hyperbolic medium. But these modes are evanescent in the far field, so we couple a dipolar emitter and a suitable antenna on the top, so that we can get directional emission from these structures. So we optimize the structures. We did this with single quantum dots. These are cadmium sulfide selenide quantum dots, or we have NV nanodiamonds, with NVs in them. And we showed that we can get 200 times enhancement, and 40% collection efficiency is what we have reported. So this we have extended to study what are the materials which are more suitable to make these metamaterials from the point of view of stabilizing these nanodiamonds or quantum dots, so that the blinking and the photo bleaching effects are not dominant. So we made these hafnium dioxide based structures, and we showed single photon emission from these devices in a directional fashion. Right. So we also proposed a noon state generation. So this is again plasmon mediated. If you have two quantum dots which are embedded in a dielectric, and when it is brought close to a metal surface, the emission from one of the quantum dots excites the plasmon mode, and that couples these two quantum dots together. And the emission from these things, we showed that it comes out in a noon state. So both the photons will either be in detector 1 or in detector 2 geometry. So the other metamaterial which we are working currently is the bound state in continuum. This is well known from 1940s. Like, so people, we're known in semiconductor physics point of view that if you have a potential well, so you have these discrete energy levels and you have a continuum. Right? However, if you have a rough barrier, for example, so within this continuum, you can have a bound state. And this is a bound state in continuum, which was proposed and theoretically way back in 1940s. Right? So this is well known in microwave community also for decades. But over the last 15 years or so, this has become popular in metamaterial community because there is no metals involved in this. The metallic losses are not involved. So here the idea is that like you can have a symmetric scattering element. And if you look at the dipole and higher order multipoles, the vector sum of them will make sure that in a symmetric case for normal incidence, your dipole will be dominant and the vector sum will give you the scattering or emission in one particular direction. Similarly, we can have a random shape of this particle scattering element, and the vector sum of these, you can design it to come at one particular angle. So what this means is that like if you have a dipole emitter inside this medium, you can have directional emission. And in addition, mathematically, these are high Q or in fact, these are infinite Q factors. Zero line width mode is mathematically for these BIC resonances. So you can make use of it to have strong light matter interaction to get large emission and also directional emission from these things, from these BIC resonances. Another interesting thing is this is of vectorial nature. I'll show some example of this. So we showed a symmetry protected BIC. So this is, as I said, like, so this only happens for normal incidence. These are TiO2 pillars or discs on top of glass substrate. So at normal incidence, you have zero line width. This is a BIC resonance. If you change your angle, you're going to high Q, but not infinite, but high Q and finite line width modes, which are called the quasi BICs. And if you go further away from the normal incidence, you see these leaky modes, which are coupling to the far field, and they have much smaller Q factors in this case. Right? These have asymmetric line shapes. And right now what we're looking at is controlling these high Q modes with magnetic field. So we made this bismuth doped yttrium iron garnet. This is a ferromagnetic material. So we made these discs with ferromagnetic materials, and we are looking at controlling the emission of single photons in the orbital angular momentum states. Right? So this is one way to check whether at resonance we have spherical symmetry or circular symmetry, and if we move away from resonance, we have in the far field we see this reflected spot to show this square pattern. Right? So this is yeah, as I mentioned. So the near field profiles show this vectorial nature. You have the interference patterns which are seen in the near fields. Right? So the other work which we do is on single photon detectors. So this is work being done at NPL. So we have optimized the thickness, few nanometer thick superconducting thin films. These are the different materials which we are working on. And we use an FIB or an electron beam lithography at IIT Delhi to make these meander structures. So these nanowires basically are used for SNSPD devices. So we did optimize these device structures, and then measured the light response from these structures. These are showing optical response. Now the idea is to improve these designs to have better electrical and optical coupling from these structures. Right? So the other work which I did at TAFR is to design these so-called silicon photomultipliers. These are array of silicon APDs. So we are looking for a foundry to make these structures. So yeah, these are electrical and optoelectronic response we calculated, and based on this, like, so we optimize the designs for this work. Right. Just to summarize, so metamaterials are a combination of metal and dielectric or all dielectric scattering elements with sub-wavelength features. So what I showed is that light matter interaction beyond this perturbative regime is possible at ambient conditions and in metamaterials with embedded dipoles. Right? So I showed example of weak, strong, and ultra strong coupling regimes, and showed the single photon emitter based on hyperbolic metamaterial and long range exciton-exciton coupling mediated by surface plasmon polaritons. So we're working on currently at single photon metrology. This is the lab which we are setting up. When we look at the model deep, like, so there are features which come, especially if you have more than one photon. Multi-photon features are to be resolved properly. So we are setting up those methodologies for characterizing the few photons or the Fock states. And we're also looking at developing single photon detectors. These are the people whom I collaborate with. So the ones on the left are from my group. The blue ones are the ones currently working in the group. And these are the theoreticians whom I work with, the blue names. The funding is from TIFR and DST. And one last thing is that, like, I'm now have a new collaboration with Professor Jaslin from IIT Delhi. So we are looking at lithium niobate on insulator-based architectures for single photon generation or entangled photon pair generation and applications. So we're looking at waveguide-based ones. So unlike using lithium niobate bulk materials, we're looking at architectures where lithium niobate thin films are to be used. So this project is sanctioned, and we're looking for motivated postdoc PhD students and GRS. Thank you.
Thank you for a nice talk. So Achanta, any questions?
Okay. May I ask one if...
somebody in the audience is asking. So
yeah. Okay.
So we did at multiple sites at the edge. So the sample is a patterned metal and with neighboring unpatterned metal region, right? So from the edge of from the border and away center, right on the other edge, right at different corners, we did all these measurements, and we do not see any difference in the measurements. And on the results, the spectra or the lifetime measurements do not show any deviation. Right. Right. I mean, I've not done that thing, like, so because we have done multiple, I'll just check it out, because we do scan through the near fields, right? In the near fields, as you know, it's only certain region, like, so 10 by 10 micron or something, like 20 by 20 micron, I can scan at a time. So, and from that, like, so we have multiple scans of hundreds of scans which are there, right? So I can get those statistics, whether every time the same dot is getting excited or not. The problem with these quantum dots or even the NVs in nano diamonds is that, like, because the surface is a defect, so there's always something known as blinking, right? So the electron gets trapped there, and unless it returns to the dot core, so you don't see any emission coming out from that, right? So there can be variation, right? because of the properties of the dot, but from interaction point of view, I do not see if there should be any. There's one online, right?
Yeah, online question. Can we have? Is the online person?
Oh, okay. Yeah. So this question is regarding that van der Waals interaction potentially showed, that is minus C3 divided by ZQ.
Right.
So usually measuring C3 quotient is very difficult. So though there are a few measurements are available, but mostly people use from the calculations. And when people do the calculations, they basically assume that the material is perfect conductor. So there are several calculations we have performed by considering material media, and we found the C3 coefficients actually they depend on the material properties. So do you think that they are that sensitive that you do need very precise calculations, or they are irrelevant?
Right. We
Could you
did
please
precise
comment on that?
calculations. We did precise calculations from the point of view of exact material parameters because of our
What
extensive.
material you had considered? Could you please?
So, as I mentioned, so we considered both gold and silver because we have extensive work on these plasmonic applications. So we need these gold NNK values, for example, or the
In
silver.
fact, we have also done the calculation, of a rubidium atom interacting with the gold and SiO2 and all these metal also with the perfect candidate conductors. That's a
Right.
PRA paper. I don't know whether you have.
It is not. Please understand, it is not perfect conductor. We take the actual measured parameters.
No, that is what I am saying. So actually, for
There's
us
always
that
be
is
difference.
interesting. Yeah. So we want to verify that because we have done the calculations with considering gold as material media also. We have performed.
We can do the. I mean, if you send the design parameters, what are the dimensions? We can do the calculations.
Okay, I see. Okay, so in the calculations, when you do the C3 coefficient calculations, basically one used to use this, dipole polarizability with imaginary frequencies. Are you going to use? Are you using similar kind of formulas, or you are, using it?
We do finite difference time domain calculations where we do exact material parameters. So there are no approximations other than the
so you
boundary
also
conditions.
take into account the permittivity of the, that material.
Maybe we can
Absolutely. Right.
move the
Okay.
discussion.
Yeah, thank you.
Okay, we do have one more question. Let's take.
Right. So we use combination of electron beam lithography and reactive ion etching, or we do FIB. Right. So depending laser patterning somehow is not. I mean, within whatever we tried in the lab, they're not as good as what we do with electron beam lithography. So we did the early, I mean, the strong coupling patterns which I showed with anti-crossings, they're all done with interference lithography, which we have in the lab. Okay. Yeah.
So Gopal, anyone working on photonic processor? You have all the three components I can see with you. So who is integrating them?
No one yet. So
you should, right? So
yeah.
I think you have all the necessary tools.
Okay. See a couple of more questions. Right.
So what is the reason why you have chosen that particular ferromagnetic material?
Oh, again, we have been working on magneto-optics or magnetoplasmonics, plasmon-mediated enhancement in optical properties, both the Kerr and Faraday effects and ellipticity and all that. So the epsilon, that is a tensor. So the off-diagonal tensor components lead to the magneto-optical effects. So if you look at Kerr effect, for example, epsilon is proportional to the polarizability times the gyration factor times the applied electric field. So the gyration factor for fully substituted bismuth, right, is the highest which is reported in the literature. So we go to bismuth 2.7 and yttrium 0.3 kind of thing. Right, right. With magnetic field control so that we can. Yes, we do. I mean, when we make the samples, we use both so that like we can compare.
One last question, I think, before we wrap up.
That thesis work which I showed, Silicon PM, that was done, the thesis was done in 2016. From then I've been trying after Bell. They made one sample, but then they goofed up with the top anti-reflection coating, and because of which the quantum efficiency which we could get was only 5%. After that, they never made the second. Right? So yes, I'm looking for industry who is willing to take the design and make it.
All right. Thank you again for that very nice talk.